Sorry? Q elements and then projective line Q plus 1, yes, yes. But when we parameterize, we don't consider infinity. So there are Q elements, okay. Each element is a representative of a class, as we all know from our knowledge of the finite fields. So corresponding to each element then, we have a theorem which says corresponding to each theta, that is element of the FQ field, there is a class of certain types of homomorphisms which represent the action of the modular group on projective line over finite fields. That's a very powerful result, because then it gives us a method by which we can actually control the action, or even we can then fiddle with lots of characteristics of this action and come out with something of our choice. So for each theta that is element of FQ, which are Q in number, we get a class of certain type of homomorphisms. They are called non-degenerate homomorphisms. What it means is that the homomorphisms which do not annihilate, which do not destroy, which do not kill the generators of the modular group when we take them to the other side of the image space. So these homomorphisms give us conjugacy classes of homomorphisms on one side, correlated or parameterized with the elements of FQ. A system then was developed in form of a theorem, of course. This is what I've said, one-to-one correspondence between theta and the non-degenerate homomorphism, the class of the non-degenerate homomorphisms. When I say class, then there is a diagram related to this. If you look at a finite diagram and you don't label the vertices, then it means basically you are dealing with the diagram of the representing the class. But if you label the diagram with vertices, with elements, then it means you are talking about a particular element within the class. That means the diagram is actually representing just one non-degenerate homomorphism, which is an element of a certain equivalence class. So the interesting thing here is then you have the privilege of dealing with one diagram as a representative of the entire class if you do not bother about the labels of the vertices. That is, basically, the diagram becomes more important rather than the labels of the vertices. So just by looking at the diagram, you know that it represents a certain group, right? A permutation group, and not and that group is basically picked from the class of similar groups. So it's a very general situation and very happy situation, really. This is an example or some particular cases. Always, whenever we take action of the modular group on projective line over finite field or Galois field, you remember now for each element of the Galois field, that is theta, there is an equivalence class of non-degenerate homomorphisms depicting the action of the modular group on projective line over finite field. Diagrams of these cases without labels are important for us now, rather than the diagrams with labels. In that case, whenever we take element theta from FQ, our XY, the two generators, their product, it becomes of order 2. So in that case, the group we get, the group theorists know, in that case, the group we get is S3, because it has two generators XY. Of course, XY is XY, X square is equal to 1, Y3 is equal to 1. They all, in every case that happens. And then there we have xy to the power 2 is equal to 1. That is, xy is of order 2. And this is the definition of S3. So if we have theta, we have S3. If we have theta minus 1, in that case we get xy to the power 3. That's A4. When we have theta minus 2, then we get xy to the power 4, and that is our S4. When we have theta square, when we have a theta, the element fq, which is solution of this equation, in that case we get the order of xy as 5, which is A5. And then in the case, and these are all finite groups. When we take theta is equal to 3, if you remember, theta is equal to 3 was missing, theta 0, 1, 2, and 3 was missing. When come to 3, we get the order of xy to the power 6, always. Whatever q you take, whatever Galois field you take, you always get these 5 cases, always like that. So we have to discuss them separately. So if there is a paper or there is a research work which deals with this problem exclusively, there is a reason of doing that, and we are not breaking the sequence of results that we have been getting over the years. So there is a mantak, there is a logic in it, that we deal with them separately. Once you do that, you realize also that beyond this line, 2, 3, 4, 5, and then beyond 5, you start getting infinite cases. Basically, they represent 3 types of groups: hyperbolic, parabolic, and elliptic. In this case, we are getting the first elliptic group or space that it's dealing with. And if you do like that, you realize that beyond that, we start getting infinite groups. The first case then you look at is what happens when xy to the power 7 is equal to 1. And that's a very important family of groups. It's a branch of Hurwitz groups. Master Condor had earlier work on it by taking the action of the modular group on finite sets and using coset diagrams, which were basically idea founded by Graham Higman. So he had already produced a result in which he said that Hurwitz groups are certain Hurwitz groups. A very large quantity of Hurwitz groups are basically homomorphic images of the alternating groups. A very powerful result. Well, that comes beyond that.